Hello, in this video I'm going to explain how to translate graphs, how to take a position versus time graph and figure out what the velocity and acceleration would be at any given point of that graph. First off, the content and language objectives is I can translate position versus time and velocity versus time graphs. A language objective is I can write an explanation of how translating graphs shows the relationship between position, velocity, and acceleration. First off, before we begin translating graphs, there's a lot of background stuff you need to be familiar with graphs. You need to be able to figure out a given data point on a graph, and you also need to be able to figure out slope of a graph. And so we'll use a couple graphs to go through some examples. Question number one, it says, what is the position at 30 seconds? Again, time is on the x-axis, and then once you hone in on 30 seconds, you can figure out what your position would be. It's 8 meters here. What's your position at 14 seconds? Again, hone in, crosshairs on 14 seconds. And then again, you see that the y value would give you your position, which in this circumstance is -2 meters. A little more difficult of a problem, what's the velocity at 35 seconds? What velocity is on a position versus time graph? Velocity is the slope of your line. And so you have to figure out where 35 seconds is. And then what you need to do is figure out your rise, what's your change in y value, your run, what's your change in x value, and calculate your slope by taking rise divided by run. In this case, the slope is 0 because the plateau here, it's flat from letters E to F. Finally, what's the velocity at 26 seconds? Again, figure out where 26 seconds is, and then find some coordinates that you can use to calculate rise and run. You can see your rise, you move up your y value 10. Your run is 10, and so your slope is 1 meter per second. That would be your velocity in this section of the graph. You can do the exact same thing for a velocity versus time graph. What is the velocity at 10 seconds? Again, just coordinates, make a little crosshairs here, and you can see that the velocity is the y value here, would be 2 meters per second. What's the velocity at 15 seconds? Again, this is a velocity versus time graph, and so coordinates show that this is -4 meters per second. What you can also do is figure out what the acceleration is at any given point. And so the slope of a velocity versus time graph shows your acceleration. And so at 10 seconds here, just like the first circumstance we looked at with position versus time, you see that there is no slope here because this is flat. So the acceleration at 10 seconds would be 0. What is the acceleration at 13 seconds? Again, key in on 13 seconds. And then you can calculate the rise and run of this section of the graph. The rise is -6 because you're moving down. The run is 1.5 seconds. And so your slope is -4, and then your acceleration, therefore, is -4 meters per second. Translating graphs, this is just an example of kind of how this process is going to work. Is again, if you're given on the top here a position versus time graph, you can figure out what the velocity is at any given point. If you want to look at all the specific examples here, please do. But we'll spend the rest of this video explaining how to get from the top portion of this graph to the bottom portion of this graph. First off, when you're translating graphs, the general pattern that you will see, and we'll keep on coming back to this, is that curved lines become sloped, slope lines become flat at whatever that slope is, and then flat lines become flat at 0. And again, I'll go through lots of examples to show you this. But as you move from a position to velocity or velocity versus time graph, curved lines are going to go to slope, slope to flat at whatever that slope is, flat go to flat at 0. And so you can look at this particular example, and you can see on top, the first section of the graph is curved. That below becomes sloped. The next section of the graph, you have a slope section that becomes flat at that particular slope. And then at the very end of this graph, you have a flat section that becomes flat at 0. Again, these circumstances as you move from on the top, a position versus time graph, to on the bottom, a velocity versus time graph. Again, just to illustrate this through a couple examples before we get to a practice problem. Position versus time graph on top, you have a slope section. That slope section for your velocity versus time graph becomes flat at that slope. And then that flat section for velocity versus time graph becomes flat at 0. A curved section becomes sloped, becomes flat at that slope. Steps for translating graphs, what I always like to do is to break a graph into segments, to label each segment as curved, slope, flat, or flat at 0. Keep in mind that whatever time segment you're working over is going to be continuous from one graph to another. Do the whole curve to slope, slope to flat at 0 thing. And my recommendation is to save any curved sections for last and play connect the dots. And I'll explain that in just a moment. So my example I'm going to use here, I'll break it into step by step how I do this. Number one, break a graph into segments. We've got 3 different segments here that are already labeled for us. 2, label each section as curved, slope, flat, or flat at 0. And so you have a slope section, a curved section, and then a slope section. 3, keep in mind that time always stays the same. So section A is 2 seconds, section B is 4 seconds, and section C is 4 seconds. So that's going to be the same for the velocity versus time graph. Then what you're going to do is follow that pattern of curved to sloped, sloped to flat at that slope, flat to flat at 0. And so what that means is for each of our slope sections, we need to determine what the slope is. For the section A that's listed here, we have a rise of 6, a run of 2, and so you have a slope of 3. For section C, you have a rise of -4, a run of 4, for a slope that's -1. Then what you can do is you can add in those flat sections at what their slope was indicated. Numbers aren't shown on the y-axis here, so I just used each box to represent 1. And so I added those numbers. Your final step is to save curved sections for last, play connect the dots to create your translated sloped line. And so you have that section in the middle that's blank. It's supposed to be a slope line. Students are more successful if they save that for the end and then connect the dots. You can do this exact same procedure to move from your velocity to acceleration versus time graph. So I'd say go through, try this yourself, see if you come up with the correct answer. But repeat those steps. And what you come up with for an acceleration versus time graph should be what you see right here. Because our flat section became flat at 0, our slope section has a slope of -1, and so you have a flat section at -1 here, and then a flat section becomes flat at 0. What you should notice is that it becomes easier as you move from velocity versus time to acceleration versus time, because you shouldn't have to deal with any curved sections. And what you might notice here is the only points that you'll have any acceleration as when you had a curve on a position versus time graph, because curves become slopes, slopes become flat at that slope. That's the end of this video explaining how to translate graphs from position to velocity to acceleration versus time. If you have any questions, please feel free to stop by during homework help hours or period 1A. Thank you very much and have a great day.